You are most welcome to our lesson this morning. I told you that today we shall be doing a review of the work that we have studied as we prepare for the test. Like the test this time will again start from our work on sorts. The test will include sorts, it will include chemical families, and it will include structure and bonding. Sorts, chemical families, then structure and bonding. Jekwa, so if you unmute your gadget again, I'm likely to remove you because we are getting a lot of feedback from that side. So you remember when we started from sorts, we defined a sort. This is just to remind you, a sort as a compound formed when either it can be all or part of ionizable hydrogen of the acid is replaced by a metallic ion or ammonium ion. That's how we defined a salt. I think you remember. It is a compound formed when either all or part of the ionizable hydrogen of the acid is replaced by a metallic ion or ammonium ion. That's how we defined a salt. We said we have two types of salts. You will not be going through everything, but the most important part of the work. We said we have two types of salts. We have a normal salt and an acid salt. Told you those two are very important, and it is very paramount that you know the definition and examples of each. Normal salt, we said it is the one formed when all the ionizable hydrogen of the acid is replaced by a metallic or ammonium ion. So the key word there is all. For example, we look at hydrochloric acid. So when all the hydrogen of hydrochloric acid is replaced by a metallic or ammonium ion, the salt formed is now a normal salt. So what is important is for us to remember that for a normal salt, all the ionizable hydrogen of the acid is replaced. All the hydrogen of the acid is replaced by a metal or ammonium ion. And the metal can be any metal. It can be sodium, it can be hydrogen, magnesium, aluminum, etc. So these salts do not contain ionizable hydrogen. Examples of normal salt, we can have sodium chloride. In sodium chloride, it means that all the hydrogen of hydrochloric acid has been replaced by sodium metal. Magnesium sulfate, it means that all the hydrogen of sulfuric acid has been replaced by magnesium. So that is a normal salt. So keep on sending your questions, even in inbox. Wherever you don't understand, don't relax. Send questions even in my inbox. I will always answer you. We have acid salts. We are defining an acid salt as a salt formed when only part of the ionizable hydrogen acid salt. So not all hydrogen in acid salt will be replaced by a metal or ammonium ion. For example, in sulfuric acid, eh, if one hydrogen is replaced by sodium, then we shall form sodium hydrogen sulfate. If one hydrogen is replaced by ammonium ion, that's why, no, this, if one hydrogen is replaced by sodium, we shall form sodium hydrogen sulfate, and that will be an acid salt. Now, this is carbonic acid. If one hydrogen is replaced by calcium, we form calcium hydrogen carbonate, and that will also be an acid salt. So, acid salt, we are saying it is the salt formed when only part of the ionizable hydrogen of the acid is replaced by a metallic or ammonium ion. So note the difference. For a normal salt, all the hydrogen of the acid is replaced by metallic or ammonium ion, and for acid salt, only part of the ionizable hydrogen is replaced by ammonium or metallic ion. Examples: sodium hydrogen sulfate, meaning this one is coming from sulfuric acid. Calcium hydrogen carbonate. Note the formula that the valence of calcium is 2, whereas the valence of hydrogen carbonate is 1. So this is the correct formula of calcium hydrogen carbonate. So let us now go to solubility of salts. We define the solubility as the amount of salt. Solubility is the amount of solute in grams required to saturate 100 grams of solvent. In most cases, the solvent is water. So that's why in bracket we are putting water. So solubility is the amount of solute in grams required to saturate 100 grams of water at a particular temperature. This word saturate, it means you make the solution concentrated such that the solution cannot dissolve any more solute. I was giving you an example that when you add sugar to water, it will dissolve and will form a solution containing a solute and a solvent. But if you continue adding sugar, a time is going to reach whereby the solution of sugar cannot dissolve any more sugar. So at that point, when the solution cannot dissolve any more sugar, we say the solution is saturated. Yeah? The solution is what? Is saturated. So a solubility, it is the amount of solute in grams required to saturate 100 grams of solvent, which is usually water, at a particular temperature. This word must be there also, then at a particular temperature, because solubility changes with temperature. So from there, we looked at an experiment to determine solubility of a salt, you remember, but all in all, what was important was the calculations. Let us maybe try to look at this example. It will help us to remember how we used it to determine the solubility. For example, 30 grams of sodium chloride was dissolved in 75 grams of water. The most important thing is to know the mass of the solvent. And the mass of the solvent is water. So the mass of solvent is 75. And the solute now is sodium chloride, whose mass is 30. Then, if you have that, what you need now is the definition of solubility, which says solubility is the mass of solute in grams required to saturate 100 grams of solvent. So here it means that 75 grams of water dissolve 30 grams of sodium chloride. That's what the statement tells us. So you will now need to know the mass of sodium chloride that will dissolve in 100 grams of water. And that is how the definition goes. Mass of solute required to saturate 100 grams of solvent. So instead of 75 grams of water, we should now find the mass which will be in 100 grams of water, and that will be the solubility. I think you are getting my point. So we say 75 grams of water dissolve 30 grams of sodium chloride. So what about 1 gram of solvent, which is water? Then here we divide by 75 on both sides. 75 here, 75 by 30 to have 1 gram. So 1 gram dissolves 30 out of 75. Please, those who are joining in, you are free to interrupt and ask a question anytime where you are confused. You are allowed. Just say, excuse me, and I will give you a chance to ask your question. So 1 gram of solvent dissolves 30 out of 75, and therefore 100 will dissolve 30 out of 75 times 100. In other words, we have multiplied by 100 both sides. So by 100, 1 by 100, and 30 out of 75 by 100. And we get the answer as 40. So that is how we do it. Always follow the definition: mass of solute required to saturate 100 grams of solvent. But we said there can be cases where they don't give you the mass of solute directly. Where they don't give you the mass of solute directly. For example, they are telling you that 12 grams of potassium chlorate was carefully evaporated to dryness. Evaporated to dryness, this means you are removing water. So when 12 grams of potassium chlorate is evaporated to dryness, it means we are driving off the water, and we shall remain with mass of pure salt, which is potassium chlorate. So 2.4 grams of potassium chlorate were left on the evaporating dish. So it means after removing the water, you remain with 2.4 grams of pure potassium chlorate. So that means the mass of water alone will be 12 before evaporating. You subtract 2.4 after evaporating, and that will be the mass of water. So you have now the mass of water or solvent as 9.6, and you also have the mass of the salt as 2.4. And you follow our procedure to get the solubility now. Say 9.6 grams of water dissolve 2.4 grams of potassium chlorate, and 1 gram of water, it means we divide by 9.6 by 9.6. 1 gram of water will dissolve 2.4 out of 9.6. And 100 grams, it means we now multiply by 100 by 100, and that is what we get. That is what we get there. 2.4 out of 9.6 times 100, and the answer is 25. Now, from there, there is something we looked at about the importance of solubility curve, uses of solubility curve, and we said that it can be used to determine the mass of crystals deposited when a solution is cooled from a higher temperature to a lower temperature. Solubility curve can be used to calculate the mass of salt obtained by cooling a solution from a higher temperature to a lower temperature. And how did we say we get the mass of crystals deposited? We said we get the solubility at higher temperature and we subtract the solubility at lower temperature. I think all that work you remember. I'm just reminding you more. Get the solubility at higher temperature and you subtract the solubility at lower temperature. For example, if a salt P with solubility 180 grams per 100 grams of water was cooled at 30 degrees, so it was cooled from 90 to 30 degrees. So the mass of crystals here will be the solubility at 90, which is 180. You subtract the solubility at 30, which is 25. Simple as that. And you get the answer as 155. So it means this is supposed to be 45, not 25. Don't get confused. Now, we had to look at the most important part on salts, and that is preparation. You people, I told you to take time and go through that work thoroughly and make sure that you understand it very well. So, solubility, preparation of salts, you must know the solubility rules. Some salts are soluble and some salts are insoluble. Now, I will quickly remind you about the solubility rules. All potassium, sodium, and ammonium salts are soluble in water. That was number 1. Anything that has potassium, sodium, and ammonium is soluble in water. It can dissolve in water. Number 2, all sulfates are soluble except 2 sulfates. 2 sulfates do not dissolve in water. That is barium sulfate and lead 2 sulfate. But we also said that calcium sulfate is sparingly soluble. Chlorides, we said all the chlorides are soluble except lead 2 chloride and silver chloride. But lead 2 chloride is soluble in hot water. I think you remember that. All nitrates are soluble. Anything that has a nitrate is soluble in water. All nitrates are soluble. Then I think that is it. So, preparation of salts depends on whether the salt is soluble or not. we said soluble salts are prepared by crystallization and neutralization. Remember, we use neutralization to prepare salts of sodium, ammonium, and potassium, whose carbonates and oxides are soluble in water. So neutralization is only for salts of sodium, potassium, and ammonium. I think you remember that. Crystallization is for soluble salts, whereby we use an acid either on a pure metal or on a metal oxide or on a metal carbonate or on a metal hydroxide. That is crystallization. Then insoluble salts have only one method of preparation, and that is precipitation or double decomposition. So double decomposition is just another name for precipitation. It's just another name for precipitation. It's like saying Baidi Kevin. If I say Baidi, it is still one person. Kevin, still one person. Get that? So precipitation and double decomposition mean exactly the same thing. So I will only remind you about the general methods. For preparation of soluble salts. These are the general methods and they don't change. Number one, place a dilute acid in a beaker. We always begin with the acid, you put it in a beaker, but the choice of acid matters a lot. I've seen in most cases, some people, I tell you to prepare zinc chloride, then you find someone using sulfuric acid. Are you mad? You want a salt which is a chloride, you must use hydrochloric acid. You want a salt which is a sulfate, like copper 2 sulfate, then the acid to be used should be sulfuric acid. You want a salt which has a nitrate, like lead 2 nitrate, the salt to be used must have a nitrate. So place some dilute acid in a beaker, then warm the acid. Warm the acid. Why do we warm the acid? I told you we warm the acid to increase the reaction such that the reaction can go on faster. So warm the acid and add the metal. So if you are using metal, you add the metal. If you are using metal oxide, you add the metal oxide. If you are using metal hydroxide, you add the hydroxide. And if you are using metal carbonate, you add the metal carbonate. But you add it bit by bit or little at a time until it is in excess. Glory is asking, what should we use for nitrate salts? When you are preparing a salt which has a nitrate, you must use nitric acid. Nitric acid, whose formula is HNO3. You must use nitric acid. So warm the acid and add the metal or metal hydroxide or metal carbonate, but we said it should be little at a time while stirring, to ensure that the acid is completely used up. So you add a little at a time until in excess. We also said that the word excess can mean until the metal or carbonate you are adding does not dissolve any further. That's what it means by excess. Then when you add excess metal or metal oxide or metal hydroxide or metal carbonate, you know, if it is excess, it means some of it has not dissolved. So you will filter off the undissolved metal or metal hydroxide, eh? Or excess metal or metal hydroxide or metal oxide or metal carbonate, and you will obtain the filtrate. Who can tell me what you do to the filtrate? After obtaining the filtrate, what is the next step? Suvi, what is the next step? Come on, faster. Someone tell me. After filtering off the excess metal, and you have the metal oxide or metal carbonate, and you have collected the filtrate, what is the next step? What do you do the next? What do you do to this filtrate you have obtained? Teddy.
Saturate the filtrate by evaporating and allow the solution to cool as it cools to form the salt crystals.
Repeat, you were very fast.
Saturate the filtrate by evaporating and allow the solution to cool as it cools to form the salt crystals.
Good. Yeah, you people are very good. Thank you for understanding the concept there. I'm very happy. So, after obtaining the filtrate, you saturate the filtrate. To saturate means to drive off the water. So saturate the filtrate by evaporating on an evaporating dish. And after saturating or driving off the water, you allow the saturated solution to cool, and as it cools, it forms crystals. What do you do to those crystals? Filter off those crystals and wash them with distilled water. Then dry the crystals by placing in an evaporating dish. So I'm still saying the procedure is that, and it is not going to change. Only that be keen before you start writing. Ask yourself, are you preparing a soluble salt or insoluble salt? Then, which two substances are you going? Choose the correct acid and follow the question. If they are telling you to use a metal, add a metal. If they are telling you to use an oxide, add an oxide. They are telling you to use a carbonate, use a carbonate, you people. Then, if a question is asking you to prepare a salt and you don't write the equation, be rest assured that you have lost 1.5 marks. An example is here. So prepare zinc sulfate from zinc metal or zinc powder. Clearly here the acid to use is sulfuric what? Acid. So just follow the procedure. And finally you should write an equation. Zinc plus sulfuric acid, you get zinc what? Sulfate plus hydrogen. If at all we don't specify, remember the most important point that I told you. There are metals which cannot displace hydrogen from the acid, and those are particularly metals which are below hydrogen in the reactivity series. For example, copper cannot displace hydrogen. Lead cannot displace hydrogen. So for such metals which are below hydrogen in reactivity series, we use their oxides, because their oxides are either basic. For example, copper 2 oxide is a basic oxide because it is an oxide of a metal. So if it is a basic oxide, it will react with acid. Remember, the opposite of acid is base. So a basic oxide will react with acid. For example, this metal cannot be copper. You cannot use this method for copper. Instead, if you want to prepare copper 2 sulfate, you use copper 2 oxide because pure copper cannot displace hydrogen. I think you are understanding that. So, from metal oxides, a good example is what I've been talking about here. You can be asked to prepare zinc sulfate or zinc chloride or copper 2 sulfate from copper 2 oxide. The same procedure we are following, and the equation, we shall have copper 2 oxide, which is basic, so it will react with sulfuric acid forming copper 2 sulfate plus water. Magnesium oxide plus hydrochloric acid. There I know you are okay, but I want to remind you about preparation of salts from insoluble metal carbonates. This one we also looked at it. You are preparing lead 2 nitrate from lead 2 carbonate. Again, the same procedure, and the equation is there. So instead of using pure metal or metal oxide, now you are using the carbonate, and it is still the same thing. Maybe let me remind you about preparation of insoluble salts. But before that, salts whose carbonates oxides are soluble, preparation of salts whose metal oxides and carbonates are, this word should be soluble in water. That word should be soluble. And now, when writing the formula, how do we know? That is a very good question. When writing the equation, how do you know whether a salt is aqueous or solid? You have the solubility rules, right? A salt which is soluble in water, give it the state of aqueous. Baidi asked a very good question. When writing the equation, how do you know that the salt is aqueous or solid or liquid? And I'm answering her by saying, a salt that is soluble in water, give it a state of aqueous. For example, when I'm forming zinc sulfate, I have zinc hydroxide. Zinc hydroxide is insoluble in water, plus sulfuric acid. Sulfuric acid is dilute. Remember, in our methods we say add dilute. So when you use dilute sulfuric acid, it means it was dissolved in water, so its state is also what? Aqueous. And you form zinc sulfate. Zinc sulfate is a soluble salt, so its state should also be what? Aqueous. So the water in sulfuric acid, where you are using dilute, will be the one to make this zinc sulfate aqueous. But if it was insoluble, for example, if you formed lead 2 sulfate here, which is an insoluble salt, then the state should have been a solid. Allow me to take you to remind you something about insoluble salts. Insoluble salts, we said they are prepared by double decomposition. But take note, when you are preparing an insoluble salt, you use 2 salts which are soluble. You react 2 salts which are soluble in water to get an insoluble salt. For example, when you are preparing barium sulfate, then because all nitrates are soluble, I can use barium nitrate. And I use another soluble salt that contains a sulfate. And we usually use sodium sulfate. So this is what I'm advising you. When you are preparing an insoluble salt, use a salt of sodium because all sodium is soluble. Okay? For example, here you can use sodium sulfate. You are sure that it is soluble. Then the other salt, use a nitrate because all nitrates are soluble. So when you are preparing barium sulfate, use barium nitrate and sodium sulfate. You get that? Eh? So when you mix those two, you will form a precipitate. And when you form a precipitate, because you form barium sulfate which is insoluble, just filter off the precipitate because you want the insoluble solid. Then you dry the precipitate by pressing between two filter papers. Eh? So let me ask you now, what if you want to prepare barium, what if you want to prepare lead 2 sulfate which is also insoluble? Then you should use a nitrate, that is lead 2 nitrate and sodium sulfate. You get that, you people? Use a nitrate and another sort of sodium. If you want to prepare lead 2 carbonate is insoluble, then you should mix lead 2 nitrate and sodium carbonate such that sodium provides the carbonate to lead to form lead 2 carbonate. If you want to prepare copper 2 carbonate, then you can use copper 2 nitrate and sodium carbonate. So to be on a sure, like this new song of Vinka, okubeera ku sure, you use a nitrate and a sodium salt. That is it. I wish you a good day. God bless you. I wanted to take you through salts. It is very important topic, but go ahead, read chemical families, then read the formation of bonds, ionic and covalent bonding, where we have spent a long time. I wish you good luck in the tests. Bye-bye. Those who came late, the recording is there. Bye-bye. Greet for me your parents.
Bye.